Okay. So any questions about graphs? So graphs are big in math and elsewhere. So wherever you see any kind of quantitative analysis, you end up with seeing a lot of graphs. Sometimes several graphs on one xy plane. There is a terminological subtlety here, and that is the graph versus a graph. So this is the picture at the top is about the graph of a function. So on the right, on the left, I have the function over here given by a table. Okay, so a really simple function with just a few values. Okay, so that's on the left. And then what's happening? Through this process, we build the graph of that function. Okay, so that is the relation, a very precise relation, and it works out. You can go backwards if there are just a few points, then you could go backwards, and then you can recover the original function from the graph. Okay, so function, when it's just a table, build these construct those points on the xy plane, and then you can just forget about where the table come from or where the dots came from. You read them, and you can recover the original function. So I can do it actually very quickly. So imagine that once again there is no table. How do I get back? I just look at the coordinates of the points on the xy plane. So this is x and this is y. So this point is 0, 1. This point is 1, 1. This point is 2, 1. This point is 2, 2. And this point is what is it? 4, 5. 4, 5. Okay, so they are pretty much random, but unless you read the x's, unless you move from left to right, then you can put them in order. List these pairs of coordinates. So there are a bunch of points. You order them from left to right, and then you put in that order on the list of coordinates. So I have 0, 1, a point, 1, 1, a point, 2, 1, a point, 2, 2, a point, and 4, 5, a point. And then what do? I just draw a line through like this, and then I have my table. So that's the original function. Okay, so that's possible to make a full circle when the function is so simple. It is much more complicated or virtually impossible if your function comes from a formula or any kind of other or a list of instructions, an algorithm or anything like that. Then what you do is best you plot a few points, and then somehow either by guess or your computer make that guess for you. They turn it into a curve. Okay, and that curve. It's not, you cannot recover the full function anymore. Okay, so the function is not a table anymore, but rather, put that idea somewhere. So function, alternatively, function as given by a formula, let's say. Okay, then the table becomes small rather than large, so say x and y equal x squared, then I could plot just some of these, okay, in these, and then plot them on the xy plane, so like this. Okay, but then you don't stop here. Why? Because you know perfectly well that there are a bunch of points that you have skipped. Okay, and if you have skipped them, you still want to have a general idea where they are. And this might be, your table might be actually not the table, but rather the function, the original function might be describing some continuous process maybe x is time, and time is changing continuously, and then y is the position, and the location is changing continuously. So you don't want to skip over from one point to the next. So fortunately, that's either you just use your imagination a little bit and you connect them by curves like this, or your spreadsheet or whatever graphic capability you are using will do it for you. So these points will be connected, as I did a few times with Excel, will be connected into a curve. Okay, so then the function given by a formula on the left, and then its graph is here. Now the question becomes, can you recover the function given by a formula from the graph? And the answer is no. Well, generally speaking, unless you know that it is straight lines and some very narrow circumstances, you cannot, because you can't. All you have is a lot of information there, and you can certainly get a lot of points. You can recover a table, but you cannot recover not the formula. Okay, so that's the limitation of the idea of the graph, and then so the conclusion is the graph of a function is not a function, or definitely not the function, but it's visualization. Used a lot because you have quantitative relations, you want to understand, you get to gain some insight of it, so put it in a visual way helps a lot. And so that's why graphs are everywhere. So that is the second angle, but yet a different one is speak of a graph. Okay, so you see the difference. The graph of a function on one hand, and then what does it mean to see a graph? So one way to understand that every graph is the graph of some function. That's one way to look at it. And another one is what we discussed last time, and that is the second one, we can build a function from it. From it meaning the graph. Okay, so the graph meaning the graph, that is, what is a graph? It is a circular pen. Okay, and the only like this. Okay, so that's a graph. Just on the xy plane, you have some curve drawn or something else, and then we can, or at least can try to build a function from it. That's what we did last time. So let me refresh your memory about that. So this is what we did. There is, if we look at it right here, all we have is a curve. Okay, so there is no table, there is no formula, there is no algorithm. Okay, so is there any function behind this curve? And there might be. In the if you try to write it very carefully as we did on the right, then it is actually a list of instructions that tell you how that function that is behind the graph is computed. So let's go over this one more time. So x is the input, a number. Step number one is actually plotting x as a point. So x is a number to begin with, but then we think of it as a coordinate of a point on the x-axis, and then we plot that point on the x-axis. That's the very first step. Then we draw, as you can see, a vertical line through that x on the x-axis. Step number two, find the point of intersection of that line with the graph. That graph that's supposed to be the function. From through that point, draw a horizontal line until step number 4, find its intersection with the y-axis. Take that point and find its coordinate, and that will be the output y. So using nothing but the graph, that curve, we were able to compute output y for each input x. Okay, so a function is truly, as you can see here, is a list of instructions. They're certainly not algebraic instructions, but they're fairly thoroughly describe what you're supposed to do here. The advantage of this is also when you write something very carefully, you can point out what can go wrong. Okay, so when you have a list of instructions, once again, what we did last time, we saw at when we were talking about the domain. You look at the steps and see at what point something that can go wrong. Okay, so what can go wrong? So look at the instructions and tell what can go wrong. Now let's go one by one. Step number 1, draw a vertical line through point X on the x-axis. Is there anything that can go wrong with that step? Step 1, what can go wrong? Can you always draw a vertical line through a point? Yeah?
Not at the graph.
No, that you're talking about the second step. Yeah. So you got ahead a little bit of what I was going to say, but the answer is nothing to this question. But to the second question, this same question about step 2, indeed, it is possible for things to go wrong. Because, for example, to begin with, there is no curve on the plane, and what you're looking for, look at step 2, find the point on the line that also belongs to the graph. So, well, there you go. So, no point. That could be a problem, because then you cannot finish your algorithm if you haven't found that point of intersection. Okay, so that can go wrong. But specifically, that is an extreme case when there is no graph to begin with. But there might be simply missing point. Okay, so for example, look at what I'm doing here. I pick x over here. If I pick x over here, step number 1, I draw a vertical line, and then I realize that this line has no point in common with my graph. Okay, so that is a bad x. This one is a bad x. So if it is bad x, how do we speak of it differently in mathematical language? Just like we talked about on Monday. Something breaks down. What do we say about x? It's undefined. That's another way to put it. There is a better way to put it, yes. So the function is undefined at x. What does it tell you about x? What did we talk about on Monday? What's the main topic?
Infinitely many solutions.
No, go the other way. Not infinitely many, but how many?
No solutions.
No solutions, right. So no solutions. Okay, so no solutions. The x, that line we drew, it was x is the original input. then after step 1, that input becomes the line, and that line produces no output. So step number 2, under these circumstances, does not produce any output. What do we say about x? We say the same thing as when we try to plug in 0 into 1, or x. What do we say about 0? Zero relative to function 1 or x. What is it?
Undefined?
It's undefined, yes. The word I'm driving at is the domain. We talked about that the whole Monday about domain. So when the function is undefined, it means that number is not in the domain. Okay, so that's what we have discovered. If it happens that our vertical line does not cross the graph, it means only one thing, that x is not in the domain. So even though things went wrong, but all we have to do is just to exclude that x from the domain and then move on to the next x, or if we can, go one by one. Okay, so that's fine. So that is bad x, and we excluded it. And then if we have done that many times, the way we did it yesterday, we actually tried to retrace our steps. Remember how we did it when we ended up with division by 0? I probably can find that spot. We had a sequence of operations, and we were looking for domains for the domain. Use this one. I forgot where is it? Where it is? Unfortunately, I cannot scroll. This thing does not allow scrolling. Yeah, this one. Okay, so we had our function described as a list of commands. Okay, just like we are facing now, except it was less geometric. And then we discovered that we have that reciprocal step number 3. We could end up dividing by 0, so we realized that we cannot plug in 0 into step 3, otherwise we have a breakdown. So in order to find the domain, we had to trace back that 0 in order to find which x's to exclude. Okay, and we did. Okay, and so we realized that we have to exclude x equal -2, because -2 causes 0 after the first step, and then after the second step, it's again 0, and then at step 3, you divide by 0, and you have exclude. So roughly the same thing we need to do with our operation on this graph, and here. And the step is, so to make sure how do we find how do we exclude all x's from the domain, it is very simply all the straight lines that do not pass through the graph will not be in the domain. Or conversely, the domain is made of all x's with a point on the graph right above. You can see how that point on the left, the red point on the left, has no points on the graph right above. So my graph is this green one, okay? So the red X on the left does not have anything above it, but the purple one on the right does. So this one is okay. This one is good. It has a point above it. See this? It did not break down when we carried out that computation. And this one is bad because, well, it does not have it. So that way, if you can, you go through all the possible x's on the x-axis and look up if is there a graph right above it. If there is, it's in the domain. If not, it's not in the domain. Okay. Okay. So unfortunately, that's not it. What else can go wrong at step number 2? long story short, number 3 and number 4 will not have any problems. So none here, none there, but there is another thing that can go wrong in step number 2. So we're looking for that intersection. What else can go wrong? So one will go wrong, there is no intersection. What else can happen? 2 intersections, right? 2 intersections. So that's also bad. So what's our conclusion then? This is not a function, right? Okay, so that's the whole analysis of a graph. Any kind of curve or any kind of set on the plane that you can think of, you draw, it could be a spot, it could be a line, a curve, a square, a circle, doesn't matter. You can examine it in this fashion and you'll discover whether or not there is a function there. And at the end of the day, you will have that function if it is possible. The only way it is not that function, it has 2 crossings, and then you have to discard it. Then you say that no, it's not a function. Okay, and then whatever is written in orange there, it is simply the vertical line test, right? So ultimately, just the vertical line test. Okay, so that's what we need to know about graphs, back and forth, and what they illustrate. At this point, we turn to something more algebraic, and by that I mean, so algebra, how should I put it? Algebra creates functions. So these will be the elementary numerical functions, what I'm talking about here. By the way, that graph, it produced a function that was also numerical, right? X is a number input, Y is a number output. So it is numerical even though you go through geometry. This one will be entirely about algebra. So what do I mean by algebra? It's to begin with those 4 algebraic operations. Okay, so these operations apply to numbers, and then we combine them, producing new functions. We already saw some of that with diagrams, so those were general examples. Now we want to kind of classify them and build them from the simplest to more complex. The simplest function is the simplest numerical function. What's the simplest numerical function?
X equals Y?
No, there is a simpler one. So what's suggested is this function, y equal f of x equal to x. Is that what you had in mind? Yeah. So there is a simpler one. Well, that's not a function. It is a relation, if you like, and then no, that's it. So you have to have a y in terms of x, right? So what's the simplest function? It's simpler than simply x. Well, if y has to depend on x, this is the simplest way for y to depend on x. But even the simplest situation is when y does not depend on x. In other words, what am I talking about?
Y is independent.
That's right. Independent. So not that it is independent, it is constant, which means that it's not independent really. It is just the x does not appear explicitly. So such as f of x is equal to 1, for example. That is the simplest function. See, 1, 0, doesn't matter. It is constant. So that way you don't have to, this function is more complex. So the one on the right, because changing x will change y. So there is some dependence and something going on there. But the constant function it is always the same no matter what x is. Y is the same. So that's the simplest function. So that is the technical term. Our function is called constant. If it is constant. If it has only one output. Well, as we're going to do that from now on every time, we illustrate every new function with a graph. And the graph is a horizontal line. So this is, say, y equal 2. Okay, so through the point 0, 2 on the y-axis, we plot horizontal line, and that is the graph. So there's a formula, obviously, probably f of x is equal to 2 is a formula. So a formula on the left, and then a graph on the right. Okay, so as you travel along this graph, you'll see that there is no change in the y value. Okay, so x varies, y does not. So that's the simplest case of the function. You certainly should also keep in mind that it's possible to set some more, under certain circumstances, it might be important to also have the function defined on something on a domain that is less than everything. So if you are supplied with the formula for x is equal to 2 and nothing else, then its domain is its implied domain. Remember, its implied domain is negative infinity, infinity. But it's also possible that some functions that are still constant, they're still constant. That function over here, I have over here, it's still y is equal to 2. It just happens to have a domain that is less than everything, some interval, for example. So the function is still constant. We just supply it with a different domain. So it falls under the definition. A function called constant if it has only one output. So both of the graphs over there have only one output. So both of them are constant, and just the domain might vary. Okay, so that's much we can say about a constant function. Now, then, if we move on to the next one, next simplest is indeed maybe f of x is equal to x. Probably next simplest. Okay, so the input is equal to the output, or rather, the output is the input. So nothing comes special through that. X, y equal x, like this. So nothing is happening inside. So just that black box does exactly nothing to the output. It just passes it along. Okay, so that's the computationally what's happening here. The graph. Let's plot the graph just for practice. You can jump to the. It's probably early on, probably not a good idea just to jump straight to plotting the graph. Make a little table. So 0, 1, 2, 3, 0, 1, 2, 3. Okay, so that is our table of values of our function. Not all of them, but frequently sufficient. Each row has 2 entries, and each of these rows is looked at as a point, and these were points plotted, and then usually it is enough to reveal what the graph looks like. Well, at least for these functions. So I'm plotting then, 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4, and 3, 3, that's all. Okay, so these 3 points are plotted. And you can see that they seem to be aligned on a straight line. Okay? That is only true, however, when our units are matched up. So, so the assumption of such a function f of x is equal to x is that it only makes sense when x's and y's, the domain and codomain, have the same. It's the same, pretty much same set. And specifically, maybe they might have the same units. Okay, so you cannot have a function like this when x is, say, time and y is space. Okay, so that wouldn't make any sense. You'd have to do something extra with it. By which I mean you have to. It will not be a function like this, f of x equal to x. Let's take a minute to think about that. So this is, once again, it all works out fine if I measure x and y in feet and then just plot them. That's fine. It's pretty much the same set. But what if x is, say, seconds and y is feet? Okay, so can I have f of x is equal to x? The answer is kind of no, but in a sense, I could say that I could make sense of it. For example, if I'm moving one foot per second, right, then the graph would look just like that graph over there, right? So in the beginning, I'm at 0, then after 1 second, I'm 1 foot forward, after 2 seconds, I'm 2 feet forward, and so on. Okay, seemingly it is the same function, but what's the difference? Well, the difference is units, so there's really nothing tricky there. You just have to take care of the units, but that way function is not the same anymore. So it's like this: x seconds come in, x feet comes out. Okay, so it's the same number. If you're moving 1 foot per second, then this is what you're gonna your function that describes your motion that's what the way it's gonna behave like. X, number of seconds is the input. X, the number of feet, is the output, right? So what's happening in between? Well, you just like switch the units, or that one way to describe it. In other ways, you can well, I probably will stick with that. So just change units. Okay, so the nature of these quantitates matters. So these are not just unitless numbers that you frequently see in mathematics, but sometimes it's actually, if you were talking about any kind of problem that is of any kind of practicality, then units are almost inevitable, and then you have to watch out for them and keep track of them. Okay, so then interesting idea then is whatever happens to the graph. In the graph, there is nothing wrong with the previous graph, but on the other hand, if you think about it, what is the relation between the units of feet and seconds? And the answer is nothing. There is no reason for us to think about on the xy plane makes the units of feet and seconds the same. It's all entirely relative. So I could put it like this. So these will be my seconds, and these will be my feet. Okay, so then the graph will not be, it will look slightly different. It will look like this, right? Like this. So whatever has happened to the original graph, what did I do to the original graph? Well, just compare the two graphs. What's the difference?
There's more space between each x.
Yeah, and maybe less distance in in the horizontal, in the vertical direction. This is that's exactly what happened. But I want to point out that it is wherever you do any kind of practical problem of this nature, and you're dealing with, say, data, you use spreadsheets. This is easy, right? So if there is no relation between x and y, in fact, Excel does not understand any kind of proportion between x and y. You can see those rectangles, how they change arbitrarily. Even though the data is the same, I can resize the chart, and it is the same data, it is the same graph, all the same data, all the same function, but the relation between x and y is non-existent. That's why I'm allowed to resize it anytime, and it has consequences in what follows, and that is when we start talking about straight lines and their slopes. So as you can see, if I try to connect these to a straight line, but this one is also, I missed one point here. I have an extra. So it appears to be a straight line, and that's the thing about straight lines. We can look at their slopes, but as you can see, if there is no relation between x and y, the slope is, which is supposed to measure the steepness of your graph. If I can resize the graph like this, then there is no steepness. The steepness is totally relative to my arbitrary choice of making it is wider or narrower on the screen. That's all. So then that is the relation between those two graphs. The very first graph was very specific, and because we chose same units for x and y. Then there is no other way to look at it. It has to progress at the same rate, horizontally and vertically. And that's why the slope is what? So y is equal to x has slope. Remember what slope is? Say it again. Right. Yes. Then if y is equal to mx plus b, then m is the slope. Okay. So we're getting to that, but you can look at it geometrically. And geometric definition of the slope is rise over the run. Okay, and then that is a short change for abbreviation for what's behind it, and that is the rise. You have two consecutive points, or just 2 points, on the xy plane, and then there is a change on the x-axis, and then there's a change on the y-axis, right? So, and then the former is the run, and the latter is the rise. Okay, so once again, this is rise, and this is the run. So as you can see, that's the way I did it. I have nothing but 2 points. 2 points, and then we can already speak of our slope. Why? How can 2 points create a slope? From geometry, 2 points determine what? A line, straight line. Yes, any 2 points, that goes way to Euclid. 2 points determine a line, and 2 lines determine a point. Okay, so but this is 2 points, so I don't really have to draw a line. I know that there's a line behind it. So let me draw it anyway, just softly like this. So 2 points determine a line, and then we can speak of its slope of that line in that manner. So as long as so that's not Euclidean thing. It has to be, the slope only makes sense when the axes are provided. Okay, so that's why on a piece of paper, if you draw a line, and you cannot ask the question of what is the slope, because there are no x's, and therefore there are no x and y's. There is no rise, there is no run. There is no reference point, right? So So this looks like, say, this slope might be equal to 1, but I can imagine that I have the same line. What if I supply a different slope like this? Different xy axes. On a piece of paper, I can draw any axis I want. So suppose I choose these two. Then what is the slope? What is the slope of the other one? What? Slope? The slope of the line that happens to be parallel to the x-axis. What's the slope? No. No, slope here appears to be probably 1. But now to turn your head if you like, tilt it so that your head would pointing along the y-axis. What's the slope of the pink line? It will be 0, right? So that's the thing about lines parallel to the x-axis, that they have 0 slope, and that is incidentally the slope of the horizontal line of the graph of the constant function that we started with. So where's that? If we go all the way back, we'll see that the slope is 0 because the rise is 0. So we always choose 1 to be a certain number. The 1 meaning the change of x, and rise is the change of y. Oops. Okay, so you do not want, as you can see, you certainly do not want to 1 to be 0. The rise could be 0. We just saw it, right? But this one can't. Otherwise, we end up divided by 0. Okay, so which means that vertical lines are out. We remember there is nothing wrong with the vertical line. It is a relation. So the vertical line, say x equal to 3, is a relation. And so that's a good one, but there is nothing wrong with that relation, but not a function. Not a function, then you can certainly say that maybe you can, if you want to go in that direction, you can say that slope is infinite. Okay, vertical line, the slope is infinite, but really we speak of slopes as numbers, and they should better not be infinite. Okay, so anyway, so this is the picture on the right is how you can geometrically determine the slope by examination. All you need to do, if you have a straight line on the plane, all you need to do is to look out, to pick any 2 points as long as they're not the same, and it will tell you the slope. So it doesn't matter which two you pick, you're going to end up with the same number. So like this, like that. So once again, the green one is the 1, and the purple one is the rise. So a short discussion in order here to determine why does it not matter whether or not we have which 2 points we pick. On the line. Okay, so I pick these, and then I divide the purple one by the green one. Incidentally, you also have to remember that you have to divide them. It's the change. The word change is not the same as distance. So what's the difference? Change versus distance. I mean, if you look at the triangle, then you can speak of, it appears to me that if I take this triangle out over here, if I take it out, then and zoom in, it's slightly bigger. So what I'm looking at is is a triangle, and it has two sides. One side is the green one, the one, and the rise is the other, this side. Okay? Rise and 1. Okay, so so it appears to be that the slope is then once again rise over the run, but this is not quite right. Rise over the run. So does it mean, if we say it's rise over the run, does it mean that it is a length of the vertical side divided by the length of the horizontal side? I say this is not quite sufficient. Why not? What's the difference between change in the length or distance? Well, let me point it out. Say point A and point B. So these are the 2 points from A to B. So we can speak of its slope as we are moving from A to B. Okay, so moving from A to B is that jump, and we want to understand what the rise and run of that jump are. But then we don't want to speak of distances. We want to speak of the changes of the x-coordinate and the change of the y-coordinate, and those could be negative. That's the difference. You could go down. You could go down, and then your change of x, or your change of y could be negative, and the slope could be negative, right? So if you start thinking about those triangles and distances, or rather lengths of the sides of the triangle, then you might be in trouble from the point of view of algebra and what we're doing here. So that geometry that goes way back to Euclid is just not sufficient anymore, because we're not dealing with these things on a piece of paper. We're now talking about algebraic entities, and in addition to what they did, we're dealing with negative changes as well, not only positive changes. Okay, so I'll elaborate on this next time. So the homework will be